So here's another problem that comes up a lot. We have a roller coaster going over a hill, and we want to figure out how heavy does the rider feel, or what's the rider's apparent weight, not their actual gravitational weight, but their apparent weight as they go over the hill, and also how fast could this cart go before it becomes airborne and loses contact with the ground as it goes over the hill. So let's first up by drawing a Freebody diagram here at point A. So we have the ground is pushing up. So we have a normal force going up, and the Earth is pulling down, so we have a gravity force going down. And that's pretty much it if we assume it's frictionless. So I can write Newton's law equation. So sum of the forces at A is going to be, now I'm going to call towards the center of my circle to be my positive direction, which we like to do when we're doing uniform circular motion. Just makes life a little bit easier because we can call our acceleration will always be positive then. So if I do that, my gravity force is going to be in the positive direction minus my normal force, and that's going to equal m times a. And since we're in a uniform, we're assuming we're going at a constant speed, we can say this is uniform circular motion, and this is a special acceleration, a centripetal acceleration. So now we can just start subbing things in. For part A, we can say that we have mg minus normal force equals n. Now I'm going to use the v squared over r version for the centripetal acceleration, just because usually if you're on a roller coaster, you know how fast you're going, not some, you don't take into account your angular velocity and the size of the curve in the track and all this stuff. So I'm just going to use that version for now. And it's asking us for our apparent weight, which is our normal force, just another name for the normal force. So I can say the normal force equals your weight minus mv squared over r. So there's our answer to the first part. Now part B, a little bit trickier, but also a little bit easier. It says how fast could it go? Actually, make one of the changes. Technically should be v naught, since they gave us that was the velocity. In part B, it says how fast could the rider go before the cart leaves the track at point A. So again, we can use our same relationship, our same equation. So we'll start there. So we have mg minus normal force equals mv squared over r. We're looking for the velocity this time. But we have to think about it. So as the cart goes faster and faster, if you look over here at our answer to part A, the gravity is going to stay the same. But as the cart goes faster, this mv squared over r term is going to get bigger and bigger, and the total of gravity minus that term is going to get smaller and smaller and smaller. So the faster you go, the smaller that normal force is going to be, the smaller your apparent weight is going to be. At some point, the gravity force and the mv squared over r term are going to be exactly the same size. In this case, the normal force is going to be 0. And anything faster than that, you need a negative normal force, which you can't really have in our case, because unless you have kind of locked in wheels on a roller coaster track, that's actually why they're there. So if you need a negative normal force, they can pull down and push up on the cart. But if ours doesn't have that, we can't do that. So our worst case scenario when we leave the track is really saying, when does the normal force go to 0? So if we make that assumption, we can set our normal force equal to 0 and just solve this equation for the velocity. You'll also see if our normal force goes to 0, we can cancel out our masses because there's a mass in each term now. And solving for v, we get the velocity you can need to kind of leave this track is going to be the square root of g times r. And if you did a problem about a vertical circle, you may have seen this answer before. And I'll leave it to you to think about why these two answers might be exactly the same, even though the cases are slightly different from each other.